Hey everyone, in this video we're going to talk about section 2.6, which is about the graphs of tangent, cotangent, secant, and cosecant. So in class we should have already derived the parent functions of each of those and talked about their different features. So this page just has a place for us to draw out just another period of the function. So instead of using the x interval of 0 to 2 pi, this goes from negative 2 pi to 2 pi. So it might be helpful if you want to go ahead, pause the video, and just briefly sketch out what each of these functions looks like. Okay, so we're not going to go back and fill in the domain and range because really we've already done that, but the one thing I do want to call your attention to is you should be able to recognize the shape of each graph. Okay, so like for instance, tangent and cotangent look pretty similar. It is important that you know which one, for instance, starts at the goes through the origin, or which one doesn't go through the origin. So make sure that you go ahead and you kind of memorize what the shapes look like. For secant and cosecant, it is kind of helpful to maybe look at a pattern that can be derived from them. So for instance, secant, I know is really 1 over cosine of x. I'm going to go ahead and dot in what this would look like. When I say this, I'm talking about what our cosine graph would look like on here, okay? So for instance, like I know that cosine starts at 1, and it goes down here. At pi, we're at -1. Comes back to 0, we're over here. Okay, and so similarly, cosine looks like this. So one kind of interesting pattern that we have is that if you dot in your cosine graph, that kind of tells you what your secant graph is going to look like. So for instance, the maxes and mins of the cosine graph are your maxes and mins of your secant graph, okay? And where cosine is equal to 0 means that's where you're going to have your vertical asymptote. And that should make sense to us because we know that if cosine is equal to 0 somewhere and then you have 1 over 0, well, that's going to be undefined, and so that's going to be your vertical asymptote, okay? Similarly, when we look at cosecant, I know cosecant is 1 over sine of x. If I dot in my sine graph, I have that same feature as well. Again, our maxes and our mins of our sine graph end up being the maxes and the mins of our cosecant graph. Okay, so that just kind of helps me remember which one's which. Okay, we're going to go ahead and we're going to flip over our page, and then we're going to look at this example. So for concept 1, we're going to describe the graph of the function in terms of a basic trig function, and then we're going to locate the vertical asymptotes and graph 2 periods of the function. In this video, we're going to go ahead, we're going to do example A. Example B, we are going to change a little bit. We're going to do tangent instead. We'll do that one in class next time we're together, okay? But for right now, we are going to graph 3 secant of 2x. So one thing that we need to keep in mind, we'll talk about it now. Yeah, one thing that we need to keep in mind is kind of the periods of our parent function. So for instance, when we're talking about sine, cosine, cosecant, and secant, all of those are going to have a period of 2 pi, okay, and that should be pretty normal to us. When we are talking about tangent and cotangent, those are a little bit different, and those periods are going to be just pi. We'll get to that in a second. I actually got a little bit ahead of myself, but make sure that you go ahead and write this down because that'll be helpful for later on. Okay, back to what I was saying before, though. So our function that we're looking at is 3 secant of 2x. Well, let's just go ahead and describe what's happening. First, I should know what my secant graph is going to look like. Just a super brief one. I know that it's going to look something like this, right? So when I'm thinking about that 3 here, I know that I'm going to vertically stretch 3. And then looking at that 2, well, okay, that's my horizontal compression, so I'm going to compress horizontally by a factor of 1/2. Okay, so if I'm just thinking about what the graph of my parent function is going to do, I'm going to vertically stretch up by 3, and then we're going to horizontally compress by 1/2. Okay, so basically we're going to get a lot skinnier than we normally are. Okay. So let's go ahead, let's start finding some of our features, and then we're going to make a table of values and we're going to plot. So our period, we're going to find just like we normally do. So remember, to find our period, we're going to take 2 pi and divide by b, okay? And that's true for all of these functions, sine, cosine, cosecant, and secant. If we were to do tangent or cotangent, which we'll do next class period, our period is going to be equal to pi over b. Okay, so that's just kind of important. So in this case, our period is 2 pi, and it looks like our b value is 2, so I'm going to do 2 pi divided by 2, and that's going to give me pi, okay? So that means that every pi, we're going to be repeating ourselves. For our asymptotes, well, we'll come back to that in just a second. We're going to do our table of values first. But our vertical stretch or shrink, I know that we're vertically stretching by 3. And then our reflection, well, we don't have any reflections. And remember, we'd find those reflections by looking at either one of these values if they were negative. So, no reflections. Okay, so let's go ahead. We're going to make a table of values. I'm going to slightly come over here to do it because I'm running out of room, so hopefully you're writing small. Let's make a table. Okay, and our function is y equals 3 secant of 2x. Okay, so just like we've normally done before when we were graphing our sinusoidal functions, let's go ahead. We're going to take our period and we're going to divide it by 4. And that's going to help us kind of come up with our benchmarks that we're going to do. Okay, so our period is pi. So it looks like our table is going to go by pi over 4. Okay, so we're going to start at 0, and then I'll have pi over 4. Then I'll have 2 pi over 4, which is just equal to pi over 2. Then I'll have 3 pi over 4. And then that's going to get me to pi. Okay, so we're going to go ahead and we're going to plug these values in. So I'm going to have 3 secant of 2 times 0, which is 0. Okay, so remember that secant is really equal to 1 over cosine. So that means that I could also write this function as 3 times 1 over cosine of 2x. And that might be helpful just to kind of figure out your values and using your unit circle. So I'm going to have 3 times 1 over cosine of 0, and kind of drawing my unit circle, that's going to be right here, so it's going to be equal to 1. So 3 times 1 is equal to 3. Okay, plugging in pi over 4 next, so I'm going to have 3 secant of pi over 4 times 2. That's going to be equal to 3 secant of, let's see, pi over 2. So it's going to be 3 times 1 over cosine of pi over 2. And then cosine of pi over 2 is going to be 0, so we'll have 1 divided by 0, which we can't have, so that's going to be undefined. Plugging in pi over 2, we'll have 3 secant pi over 2, so 2 times 2. So 3 secant of pi. That's 3 times 1 over cosine of pi. And cosine of pi is over here. That's going to be negative 1. So we'll have negative 3. Okay, I know 3 pi over 4 is next. I should kind of be thinking of my pattern that I have going on here. But we'll derive it out. Okay, so we'll have 3 pi over 4 times 2. So 3 secant of 3 pi over 2. That's equal to 3 times 1 over cosine of 3 pi over 2, which we know 3 pi over 2 is right here. Cosine is 0 at that point, so again, we are undefined. And then last but not least, we should get to pi. We should have an idea of what that's going to be. 3 secant, plugging that in with 2, that's going to be 2 pi. That's 3 times 1 over cosine of 2 pi. And cosine of 2 pi, again, is right here, so we're back to 1. So that's 3. So we have our values that we are going to go ahead and plot. So we have 3, undefined, negative 3, undefined, and 3. Okay, well, we'll come back to it. Okay, let's go ahead and we're going to plot these values. I see that I'm going to need to label my graph and scale it. So let's count by, well, let's make this pi over here, like this negative pi. This will be 0. Here's pi over 2, negative pi over 2, and then let's count by 1s here. Okay, so plotting our values that we have. So when x is 0, y is 3. When x is pi over 4, we're undefined, so that means I'm going to have my vertical asymptote at pi over 4. Okay, at pi over 2, y is negative 3. 3 pi over 4, we are undefined. So another vertical asymptote. And then at pi, we're at 3 again. Okay, so we've plotted all of our values in this. I don't know about you, but I'm feeling a little anticlimactic, right? Because I have all of these values and it really didn't, there's nothing I can really connect, right? I have these like just points and then we have these vertical asymptotes. I know I can't cross my vertical asymptotes. So we should know what this graph is going to look like. It's going to look something like this. However, just to be sure, we do need to go ahead and I want us to find at least 2 values that kind of fall within here. That's going to help us try to find the shape of this. Okay, so I know what it's going to look like, but I want to find just those extra points in there because I always want to make sure that I have 5 distinct points on my graph. And right now I really only have 3 distinct points because the vertical asymptotes don't count. So let's go ahead and we're going to find a value that's in this interval and another value that's in this interval. I'm going to make a separate little table. You're like, oh great, another table. Yes. Okay, so between 0 and pi over 4, let's just do pi over 8. And then in between, let's see, this would be 2 pi over 8, so then we'll do 3 pi over 8. Those will be our 2 extra values. So here we go. Okay, so we're going to have 3 secant, yep, okay, 3 secant of pi over 8 times 2 is 3 secant of pi over 4. That's going to be, well, yeah, okay, so we're going to have 3 times 1 over cosine of pi over 4. Having fun. That's 3 times 1 over the square root of 2 over 2, which is 3 times 2 over the square root of 2. That's going to be 6 over the square root of 2, which is, let's go ahead and rationalize that denominator, 6 square root of 2 over 2, so 3 square root of 2. Wow, okay, so we get to this point here, 3 square root of 2. I don't really know what that is off the top of my head. I'm going to go ahead and I'm just going to type that into my calculator. So 3 square root of 2 is approximately 243. Okay, so that means that I'm going to go ahead and graph that. So 4.2-ish. It's kind of, well, let's go ahead and erase this. Here. Okay, so that gives me this point here. And then I'm going to guess here that when we do the 3 pi over 8, we're probably going to get the negative version of that. Let's just double check. Okay, I'm just going to plug this in. Let's see where we get. 3 secant of 3 pi over 4. Okay, if I'm thinking unit circle, 3 pi over 4 is over here. So that's going to be negative square root of 2 over 2. So yep, I have the same thing, just the negative version here. So this is going to be negative 3 square root of 2, which is approximately negative 4.243. So I can graph that point. Right here. Okay, so again, I want your graphs to have at least 5 distinct points on them. That includes these other parts here. So once we have that, though, we do have this symmetry, and then we can graph the rest of our points. Okay, so what we have graphed right now is we've graphed only one period, okay? However, instead of making another table of values and doing the other half, let's just go ahead and we're going to use that symmetry that we have, and I'm going to graph just the other half. Okay, so another vertical asymptote. I switched colors. Okay, there we go. Another one. And then one more. Ooh, okay, there we go. We have it. This is what our graph looks like. I see here that it definitely is a lot skinnier than our normal graph is. So there we go. Okay, one thing we did skip over those asymptotes we've already gone ahead and we found what those asymptotes are, and I think it was helpful to look at our table to be able to find that, because I can see that that's where we're undefined. So just from the two periods that I have, I'm just going to write what my asymptotes are. So I have x equals, I have both a positive and a negative version of pi over 4. And then I have x equals both the positive and negative version of 3 pi over 4. So I have 4 vertical asymptotes here. Okay, we're going to skip over B for right now. We will do B in class later, but there's one last thing that I want to talk about, okay? Next up, we're going to look at concept 3. So we've already kind of talked a little bit about this concept before, but we're going to start bringing it back. We're going to solve for x in the given interval, and we're going to find these numbers without a calculator using our knowledge of the unit circle. Okay, so we're looking at A. So we know that cotangent of x is equal to negative square root of 3. Really, if we're thinking unit circle, there are a lot of input radians that are going to give us this out, okay? However, we've restricted this domain, so we're only looking for one specific x value that falls in between pi over 2 and pi. So if I go ahead and draw my circle, I know that the value that we're looking for is in the second quadrant here, okay? So I'm going to go ahead and I'm going to draw in a triangle, okay? And now we need to figure out how to label it. So we're talking about cotangent, and well, we should know that cotangent is the reciprocal of tangent, so cotangent is adjacent over opposite, right? If we think about our alternate version instead of adjacent opposite, and we think more in terms of x and y, I know that cotangent is equal to x over y. Okay, so I know that this cotangent of x is really equal to the negative square root of 3 over 1. That's going to help me go ahead and label my triangle. So I know that my x is going to be square root of 3, my y is going to be 1, and then making sure that I put my negative on the right spot, since I know that this is negative. Second quadrant means that our x's are negative, so I'm right there. All right, okay, so now that we have this, we are going ahead and we're trying to figure out what this angle measure is. And I know that we're looking at this angle measure in this triangle, but really remember, we always start measuring angles from over here. So really I'm trying to figure out what this angle right here is going to be. Okay, there's a couple different ways that we can do this. I prefer, let's go ahead and try to think about this in our unit circle, okay? And so our unit circle means that our radius is always going to be equal to 1. Well, if I'm going to do this, I need to kind of scale my triangle a little bit. Let's go ahead and we're going to multiply each of these by a half. Okay, so now I have 1/2, and then I have negative square root of 3. So we're looking at this point, and so I know that my x value is negative square root of 3 over 2. My y value is 1/2. So I'm trying to think, okay, well, what kind of radian gives me that point on the unit circle? Well, okay, I know it's going to be between pi over 2, and it's going to be pi. And so if I'm thinking about it, I know that the different kind of, I want to say multiples of pi over 6 would give us the square root of 3 for the x coordinate. So since I am kind of in between pi over 2 and pi, I know that this is going to be 5 pi over 6. So that is that value there. Okay, we'll go ahead, we're going to skip B for right now. We'll come back and we'll talk about that in class. The last one that I want to look at is concept 4. We're going to use a calculator this time to solve for x in this interval. So we're looking at tangent of x is equal to 1.3, and we're looking for this value of x. Again, we have a restricted domain. We want it to be between 0 and pi over 2. So just thinking about the location of where this is occurring, I know that we're going to be in this first quadrant. Okay, so I know I have tangent of 1.3. I can label my triangle with 1.3. I always kind of like to prefer it, though. I mean, it doesn't really matter. I might prefer to think about this as 13 over 10, though. So I know that tangent is opposite over adjacent, so I know that here's 13 and here's 10, and we're trying to find this value of theta. All right, okay, so in this case, I know that this is not going to follow any of my like 30, 60, 90 triangles. This is not on the unit circle. So in this case, this is where we're going to need to use our knowledge of inverse trig to go ahead and solve for this. So if you've been given this triangle a couple years ago in geometry, you would have said, okay, well, I know that this value of x is just going to be tangent inverse of this ratio, 13 over 10. Okay, and so if I go ahead and I get out my calculator and I type this in, one thing you want to do before you type this in is you want to make sure you're in radian mode. I'm going to do tangent inverse. I'm going to type it in, 13 over 10. And I'm going to get that x is equal to 0.915. Okay, and this is in radians. Okay, and I know what you're thinking. Well, why did we have to draw a triangle, and why did I have to make it 13 over 10? Couldn't I have just done tangent inverse here? And yeah, you definitely could have, because you could have done tangent inverse of 1.3 here as well. But it is going to be important within the next section to kind of think about triangle, think about what section of the unit circle we would be in to help us set this up and be able to find this angle measure. We're going to go ahead, we're going to do B as well in class, so don't do that one. Thanks for watching. I will see you all later.